go? Okay, that covers me in terms of announcements. I want to start right here with the learning objectives for today. You'll notice that some of the objectives are actually redundant. We've covered some of this material during our classes in the last couple classes that we've been together, but we are going to cover a couple of new things. And so we'll start up here working with the air and understanding atmospheric changes in the convection cycle, and then we're going to move on to the convection cycle in the ocean. And there's a really tight relationship between air and the ocean, which is why we're going to make sure that we're really buttoned up about how things look like in the atmosphere before we move on to these pieces for the ocean. So that's what we're going to do for today. I just want to start here to reinforce the basics that we've looked at already many times. The source of energy on our planet comes from the sun. Solar radiation pumping from the sun to the earth. But that's not where the heat energy comes from directly. The heat energy directly comes from conduction. So the radiation gets absorbed by items on the earth, and they get heated up. They release heat, release energy in the form of heat, and then they heat up the atmosphere and heat up other items around them via conduction. And then once that heat energy goes into the air, especially, or water, we have the convection cycle. And you'll see this one has a whole bunch of complex arrows moving around because there are a bunch of agents of change. One is density and gravity, and one is the flow of heat energy from high to low. And so we're going to keep track of all those things as we move forward. But I wanted to start here just to make sure we understand this relationship, that the sun is the big deal. This is all driven by the sun. So here's that last little small icon again, and there are a bunch of arrows going all over the place on this, and you'll see in your textbook that there's a similar, but we're going to walk through it one part at a time. We started this last time when we did the convection walkthrough through STEM, when we did that modeling exercise. But let's just make sure we still have it firm in our minds, and then we can apply it to what the Earth actually looks like and understand it. So, where is most of the heat energy concentrated? The equator, right? And the reason why is because of the exposure of the equator to direct sunlight and the number of hours on average that the equator gets, which is about 12 per day every day of the year. So we have a high amount of heat energy right at the equator. It's pushing, so the heat energy is rising, and we're pushing air particles from the surface of the Earth up into the atmosphere. Anytime we're moving particles from one place to another, so if you remember your standard definition for pressure times volume equals the number of molecules multiplied by some constant, and then there's temperature as a factor in that as well as a direct relationship. Basically what we're talking about is you're moving air particles from near the Earth up into the atmosphere. There's a finite amount of space up in the atmosphere, so if you cram a whole bunch of moles of particles into that space, you increase the pressure. So you end up with a high amount of pressure at the edge of the troposphere right out here. Things always want to move from high to low pressure. So there's all of this motion here. We're going to draw it in the northern hemisphere, but we have the same thing happening in the southern hemisphere. So air is moving from high to low pressure here at the edge of the troposphere. It's getting colder and getting denser, and gravity is working on it. Eventually we have this situation where the amount of density and gravity that's acting on the water molecules overtakes the amount of pressure that's acting on the molecules. So instead of moving more from the equator towards the poles, they start to fall back towards Earth. And the reason why is because of density and gravity. So now we've just seen all of the major elements for movement of particles due to the convection cycle, heat energy, and gravity and density. Because we're moving particles from the atmosphere and we're cramming a whole bunch of particles into a finite amount of space right here, we end up with a high pressure area on the surface of the Earth. Things are going to flow from high to low pressure right here, and so we have movement of those particles. This area, now that we're at the surface of the Earth, as we have air pressure moving from high to low, is what we traditionally think of as wind. So all of this is what we're talking about when we're talking about wind. Right at the equator, we have a high amount of rain, and the reason why is because heat energy is picking up water particles, but as it moves up, it can no longer hold those, and it's dropping them, and we have that rate occurring at the highest, that situation happening at the highest rate right at the equator. So we have a lot of rain happening in this area as well. Feel good so far? A couple quick names to make sure you can identify on the Earth. So this convection cycle on the equator, there are two of these cycles, one in the northern hemisphere and one in the southern hemisphere respectively. The one right here is called the Hadley cell. So you want to put that and file it away in your mind. From 0 to 30 degrees is the convection cycle known as the Hadley cell. From 30 to 60 degrees, again, there's another one in the northern hemisphere as well. I labeled them in the southern hemisphere, but respectively in the northern and southern hemisphere, from 30 to 60 degrees is known as the Farrow cell. And then finally, the one that's the easiest to remember is the polar cell between 60 degrees and 90 degrees of latitude. One in the northern hemisphere and one in the southern hemisphere as well. This is very important, what I just pulled up here in the box. Because the amount of energy at the equator is so great, it's the Hadley cell that powers all the other cells. So the amount of heat energy at the equator is so large that that heat energy and flow of particles into the atmosphere and then back down from the atmosphere towards the Earth is so strong and moving at such a high rate that it's actually responsible for the movement of all the other cells. So here's why that matters, and what that means is the convection cycles turn on one another like gears in a clock. So let's look at that together. If I'm here at the equator, we have movement due to heat energy pushing particles up into the atmosphere, creating a high pressure area. We move from high to low, then cold and density is moving it down, and it's pushing down, and we have movement of particles high to low here. So this convection cycle moves in this direction, and it's so powerful that it pushes the Farrow cell in the opposite direction. So we have movement from high to low here, heat energy bringing things up into the atmosphere. We have a high pressure area here, and then going from high to low here, and then cold, dense particles fall towards the Earth. And so it's cold and dense, and both cells falling right here at about 30 degrees. So you'll notice the Farrow cell goes in the opposite direction of the Hadley cell. And then the Farrow cell is what powers the polar cell, so it goes in the opposite direction of the Farrow cell, or in the same direction as the Hadley cell. But they turn on each other like gears, and it's because of the amount of energy at the equator is what drives all of the climate and weather across our entire planet. That's where the concentration of heat energy is at. Here are some of the big ideas just in review, and I really like this graphic because it shows a couple of good things, but there are a couple other parts that I don't really like as well. But let's just look at some big ideas around the convection cycle, and then we'll break down this graphic. So what we have is the convection cycle is driven mostly by gravity and density, but also heat energy. So heat energy creates lower density. So heat energy and density are related in that fashion, and then really dense particles and gravity work together to move particles from the atmosphere back towards the Earth. And so this, hopefully, we understand really well by this point. The next piece here is high pressure areas are created by moving particles. So when you move more particles into a small amount of space, you create a high amount of pressure. So more moles of particle, more matter in one area means higher pressure. And things are always going to flow from high to low, whether we're talking heat, energy, or pressure. Last piece here is, due to the Coriolis effect, when we're talking about wind especially, we're moving air particles from high to low pressure, but because of the centrifugal force caused by the turn of the Earth, we know that that's going to cause things in the northern hemisphere to turn in a clockwise direction, and things in the southern hemisphere to turn in a counterclockwise direction. So all of these arrows are hopefully starting to make sense. I just want to point this out a little bit here. There's a couple key things on this. So we have heat energy up, and then high to low pressure, and then cold density down, and then high to low pressure. So we have winds right here, a high pressure area moving towards a low pressure area, which is the equator in this respective cell. And in the northern hemisphere, as they move from high to low, they turn clockwise. And as we move from high to low here, so as you go from 30 degrees as a high pressure area towards 60 degrees, and they turn in a clockwise fashion. This part of the graphic is not perfect. drawn. So that's part of what I don't like about this, but I like that it labels the high and low areas. And the polar cell, you have high pressure here, low pressure, and they turn in a clockwise fashion. What I really like about this graphic, and the reason I put it on here, is because it shows in a nice way how it's the Hadley cell that drives the ferrule cell in the opposite direction. This is the jet stream that Mr. Hoppe mentioned last time he lectured, and it's this power from the Hadley cell that causes all the other cells to turn like gears in a clock. Feel good about this? I'm ready to do a little practice. So here we have a little practice, and I want every student to do this, and I want you to do it as though you were trying to answer a question on an assessment. This is the kind of level of things that we want you to try to be able to understand based on this. So how does all this relate to climate and weather? Here are the questions. Number one is, due to the convection cycle, where would you expect to find these different ecosystems? And I want you to label, and by where on Earth, I mean what types of latitude. And then number two is, at 36 degrees south, how would the wind be sweeping across that area due to high and low pressure and due to the Coriolis effect? There'll be a musical timer. I'm going to play it here. We're going to do 5 minutes, and then you'll turn and share. You'll know that you're at the end of the time because the music will come to a stop. Everybody should write something for this. Past halfway now. Under 1 minute now. If you feel like you have a solid answer or have got your mind around it, you can just turn and share what you think the answers are to both these. We'll go together as a group here in a moment. All right, turn and share real quick, and then we'll go over some things together. Share out, share out. All right, let's look at this together for a moment. Number one is this question about different ecosystems. Mr. Hoff is going to document in a more permanent way our answers as we talk through this, and then that'll exist after we advance past these slides if you need to look at it again. But for rainforests, where do you think the rainforests are at? The equator is a major place because we have all of the heat energy sweeping up water particles, but as it loses energy due to adiabatic cooling, we have that precipitation happening. So the equator is one of the major places. Where's another place? There's another place where we have a lot of rainforests. We have 30 or 0, 30, and then also at 60 degrees, where you see this sweeping up of particles right here between the polar cell and the ferrule cell on that edge. The heat energy is driving things up. So we also have rainforests in Europe, and we have rainforests in Canada. As a matter of fact, in Canada, there are more trees in the boreal rainforest than there are in the other rainforests found along the equator combined. They're very productive. And so we have rainforests both at 0 degrees and at this 60 degrees where we're sweeping up heat energy here as well. We have rainforests. For deserts, what are we talking about? 30. About 30 degrees. And the reason why is because as particles that are in the air that are totally dry and cold and dense, they fall towards the earth, and as they fall, they get closer to heat energy. They warm up. By the time they get to the other Earth's surface, they're dry and warm. So we have deserts usually at 30 degrees, but where else? There's another place where the descension of cold particles falls. Yeah, at the poles. Fantastic. The North and South Pole, and almost never any precipitation in Antarctica. That's a desert as well. Arctic desert. Beautiful. What about grasslands? Anybody want to conjecture about grasslands? We got 15, we got 45. I like both those answers. Grasslands is somewhere between deserts and rainforests in terms of temperature and precipitation amounts. So they're just probably somewhere in the middle, somewhere in between. And we'll learn a little bit more about that, but hopefully you were able to reason those things. Right here is about 36 degrees would be an example. About 36 degrees, there'd be equivalent in South America and in Australia. So if you're standing in this area, as the cool particles fall towards the Earth, we have a high pressure area right here. It sweeps to a low pressure area. So part of what you're feeling is the movement of winds as they go from the north to the south, because this is our point here. And then because of the Coriolis effect, they're turning counterclockwise in South America. So they're also going from the western side to the eastern side in this hemisphere. So that's where air pressure and the Coriolis effect come into play. Yeah.
Air pressure is high in that area?
It's high because it's right here. It's cold and dense, and it falls. And the falling here and the falling here is the movement of particles. So we end up with a high pressure area here, and it sweeps across the Earth from high to low pressure. This is a low pressure area here. So part of it is the movement of air particles from high to low pressure, and then it moves in this case from west to east, or counterclockwise as it were, because we're in the southern hemisphere. Feel good about that? Those are tough questions, by the way. That's the kind of reasoning we're interested in. All right. Let me go forward. Next, we're going to look at ocean gyres. And the nice thing is, now that we're moving towards water, as long as you have a good buttoned-up understanding about the movement of trade winds and high and low pressure, and that should help you understand this. There's nothing new here. It's the same type of agents of change that are causing the flow of ocean water. Excuse me. So, an ocean gyre, what we're talking about is the movement of surface ocean water across from areas from high pressure to low pressure. And the driving agent of moving this water is actually the trade winds. So on the surface of the ocean, which is close to it's the same as like the surface of the earth, we're moving from high to low pressure due to the convection cycle in the air, in the atmosphere, and so it's blowing across the top of the water. And the way I like to think about this is it's like you're blowing on a bowl of hot soup. If you're blowing on the soup, you'll notice the high pressure area is your mouth, and farther away from your mouth is lower pressure. And so when you blow, you'll see the movement of the soup actually moves, but the whole bowl of soup doesn't move. It doesn't churn up the entire thing. It only churns up the top part. So we're only talking about the movement of ocean water in the top 150 meters of the surface of the ocean. We'll talk about deep water motion here in a moment. But what's interesting is, since it's the trade winds is what's driving the ocean gyres, and the westerlies and the easterlies, things always move from high to low pressure, and they move clockwise in the northern hemisphere, and in the southern hemisphere they move counterclockwise. Here's a diagram of all of the major ocean gyres on our planet, and you see in the northern hemisphere here's the equator, right in this area. We move in a clockwise direction in the northern hemisphere, and in the southern hemisphere it's just the opposite. It mentions upwelling in the text, which is churning up all of these nutrients and minerals and particles from the lower area of the ocean along the continental shelf. And it's due as this movement of particles gets to the edge here, that churning and that motion kicks up some of the particles and brings it up. That'll be really important when we look at marine ecosystems later. These are some of the most productive marine ecosystems in the planet are in these areas where the ocean gyres are pushing up against continental shelves. So that'll come up later, but I wanted to mention it because the text introduces it as a thought here. You guys feel good about convection cycle, trade winds, and their connection to ocean gyres so far? The agent of change here, what's causing ocean gyres, is just the movement of air particles to the atmosphere of the convection cycle. All right, here's a little exercise for you, and those text boxes don't stay, but what they said is, this is a demonstration in an aquarium with room temperature water, and you pour in a jar of hot water that's in red, and then a jar of blue water at the same time that's cold in blue, and then see what happens. So what I want you to do, I'll show this video twice because it's only about 30 seconds. I just want you to make some observations based on what you see here. Let me play it again. In your observations, so people need to process it one time before they make any observations, but make some observations on what's happening and give a conjecture on why you think that's the case. Okay, let's hear from the group a little bit. What did you guys see? What happened? Yeah. Interesting, counterclockwise motion, and that was just actually due to the way that it was poured in. Oh, clockwise, sorry. Wait, did it?
It went clockwise.
Yeah. Clockwise. That was just the way that it was poured in, because one on the left side, one on the right side. But that's a good observation. I like that. What else? So she said, the first thing that I want to draw out from there is the blue falling down, which is the same thing you saw when I did the flasks of water outside. It's density and gravity. Cold water particles are denser, and they're more likely to be pulled down by gravity, so you see them plunging down. Is that new information to you or no? Is that the way that it works in the atmosphere with air? As far as you know, yes. So nothing new here. That's part of it. And then the other thing she said was the hot water particles. They poured down because it's just pouring at first, but then they moved up. And what happened after that? If the cold particles are pushing down, does that create some pressure? We're actually moving those molecules from one space to another, and so we're creating a flow. But as those particles move away, some other particles have to flow into that space to take their place. Agreed? Because this is a liquid. So is this different than what we've seen with convection cycle in the atmosphere? This is water. Is there any difference in here? What is similar about water and air? What properties of these states of matter are the same? They're both fluid, meaning they both can flow together. So what you're seeing here hopefully reinforces your understanding of the convection cycle. It's density and gravity, and it's heat energy. And as one thing moves from one place to another, something has to fill the space, and so you see an actual cycle. If you remember back to the first day, we say the movement of energy for water and for air is convection. This is convection. So what we're seeing here is not new. It's the same, but I wanted to show you in a practical way that in water, this is what we have. So the convection cycle also occurs in the ocean, not just in the atmosphere. And here's one of the key ways that we really care about the convection cycle in the ocean. I'm going to show a little video here, a different video than the one you just watched. If I can get this to go. And I have a bunch of questions here, and we'll pause it a couple times to keep track of some of the things. But the first questions I want you to keep track of is the name for this convection cycle that really matters. Thermohaline, what are the component parts? How do we get density changes in water, which they'll talk about here, and then we'll pause it. So we're just going to look at these first two questions to begin with.
The ocean conveyor belt and the Gulf Stream. Ocean currents have a direct influence on our lives. They determine our weather, our climate, and much more. The ocean currents and wind systems transport heat from the equator to the poles and operate like a large engine for the global climate. In the oceans, there are numerous currents. The so-called ocean conveyor belt is very important for our climate. This term describes a combination of currents that result in 4 of the 5 global oceans exchanging water with each other. They form a worldwide circulation system. The conveyor belt is also called the thermohaline circulation, with thermo referring to the temperature and haline to the salt content of the water. Both determine the density of the water. While the masses of water may be moved in part by wind, primarily the different densities of the global oceans are responsible for their movement. Warm water has a lower density and rises, while cold water sinks. The water's density also increases with a higher salt content. At the equator, the heat from the sun is especially strong, resulting in a lot of evaporation and thus a rise in the water's salt content. That is where the Gulf Stream begins.
Okay, let's just take these first two questions. What are the component parts of the definition? Thermo refers to what? The temperature, and then the haline is what? The salt. So these are the two things that really matter for this convection cycle, which you maybe have heard of as the Gulf Stream, but we're going to use it with its technical term here, thermohaline. So what contributes to the relative density? Well, we have to pay attention to both parts of that definition. So where do we come up with differences in density? Differences in temperature, that's part of it. So heat has lower density, cold has higher density. So that's part of it. Yes, Bree? The what? Just kidding you. The salt contents. And so if we have 5 grams of salt water in 1 liter of water, we have a certain density. But if I add 5 more grams to make it 10 grams in 1 liter, and it's totally dissolved, the 10 grams should be much denser, agreed? But another thing that we could do is, if I evaporated some of the water, if we only had 5 grams, but I evaporated it so it was down to 90 or 900 milliliters instead of a full liter, that would increase or decrease the density if we got rid of some of the water. But didn't change the amount of salt. It would increase because the proportion of salt per water would go up. That's important. All right, so next I want you to pay attention to, okay, well, how does this matter for Europe? How do we end up with movement of water from one place to another? And then this 5th question that has to do with the amount, like characterizing how big of an agent of change density is in this particular circulation.
The Gulf Stream is very important for the European climate. Its length of 10,000 kilometers makes it one of the largest and fastest ocean currents on Earth, and it's very warm. At roughly 2 meters a second, it brings up to 100 million cubic meters of water per second towards Europe. A constantly blowing wind, the southeast trade wind, drives warm surface water to the northwest into the Gulf of Mexico, where it heats up to 30 degrees Celsius. The turning of the Earth and the west winds then direct the Gulf Stream towards Europe and split it up. One part flows south, another east to the Canary Current, and a third part flows north, where it releases a lot of heat into the atmosphere as the North Atlantic Current. The water becomes colder there. Its salt content and density rise on account of evaporation, and it drops down between Greenland, Norway, and Iceland. There we also find the largest waterfall on Earth, the so-called chimneys, roughly 15-kilometer wide pillars with water falling up to 4,000 meters, 17 million cubic meters of water per second, or roughly 15 times more water than is carried by all the rivers in the world. This creates a strong maelstrom which constantly pulls in new water, and is the reason that the Gulf Stream moves towards Europe. Countless species use the Gulf Stream as a means of transport on their trips from the Caribbean to northern areas. But it doesn't just bring us animals. An enormous quantity of warm air also comes with it. In order to produce the same heat which it brings to the shores of Europe, we would need 1 million nuclear power plants. That's why we also call the Gulf Stream a heat pump. Without it, the temperature would be significantly colder here, at least 5 to 10 degrees. Instead of lush fields, we would have long winters and sparse ice-covered landscapes in Europe. In the last few years, scientists and pundits in the media have repeatedly expressed the fear that the Gulf Stream could come to a standstill due to climate change. Because if the polar caps actually melt, the salt content in the water off Greenland would fall, as would its density. The North Atlantic Current would no longer be heavy enough, and so it wouldn't sink as usual. In the worst case, that would bring the Gulf Stream, our heat pump, to a stop.
All right, so I have to go quick because we got a late start. I'm just going to talk through these points. Normally I would have had you speak to them. But if I start here with the movement of ocean water towards Europe, it's because the winds are blowing it, and it's turning in a clockwise direction because we're in the northern hemisphere. So the Coriolis effect has a role to play, and it's moving the surface water. This is just basically the ocean gyre in this area. But all along the way, we have evaporation occurring, so the density is going up. How dense and how much water is moving down in this area? A lot or just a little? A crazy amount, more than all the rivers combined on the planet. And it's falling at a really fast rate, and it's driving water. That movement is so strong that it pushes water across many of the oceans that exist on our planet. And then it starts to come back up, and the whole thing kind of drives through. You'll notice that thermohaline circulation is really important for animals, but also for human societies, industry, etc. And they talk a lot. They use the pronoun we because the people who made this video are in Germany. They're talking about Europe right here, and makes Europe a much better climate, and by much better I mean warmer, than an equivalent latitude in North America, and it's because of moving all this warm water over here. So it plays a huge role in the climate and weather regulation of this area of our planet. Likewise, these areas around Australia, the Horn of Africa, etc. Yep?
I was just going to ask about the colors, but I assume the red is awesome.
Yes, good. In the ultimate carpet sweep, this climate change thing we'll come back to later in our unit or in our class. But hopefully it gave a look. If we melt the ice, then we're changing the density. This is just the last thing I want to mention because I feel like this is from the textbook and it gives you a much better picture of what the entire thing looks like. So we have movement of warm particles here due to density and gravity. Those fall down here and it pushes. This is so strong that it pushes all along here and then we eventually have it rising. This is a giant version of the convection cycle. The most important thing here to understand is the ocean gyres only move the top 150 meters of water. This is responsible for the movement of all the other water in the oceans. It goes down to 4,000 meters, which is very, very deep in the ocean. It's crawling along the bottom of the ocean here. And so the thermohaline circulation is critical for exchange of ocean water, exchange of nutrients, and movement of all of marine ecosystems and things like that. You guys feel good about this? All right, it was a fast break there to finish thermohaline circulation. I'll see you guys tomorrow or on Friday. We'll talk about El Nino and then assessment on Monday.